the California Native Plant Society is where Bob Green and I presented the information about everything you're hearing here. And they are the #1 supporter that we've run into for nuclear power. Because as he explained, they don't want to pave the environment. So this is, we'll pass this around. This is a bigger poster that we can also send. It shows the Hinkley nuclear plant in England, which is very expensive and takes a while, has been taking a while to upgrade. That's how, it's a tiny dot. This is how much wind you need to make the same amount of energy per year. And this is the amount of 20% solar panel that you need. Now, as solar PV gets better, this can shrink. But as Dan was saying, why put it in the desert? Put it on the roofs. Caltech long ago explained that we have more sunlit humic structure in the world than necessary to generate all the peak electrical power that we need on any day. That's an important thing to understand when people start telling you about solar power towers or solar utility scale in the desert. The problem that people have to understand that they aren't told, and we run into this when we start talking to legislators who have no way of actually learning about this stuff, in California at least, because the last legislator we talked to told us that there are no standing committees or groups within the California state legislature that are tasked to gain information about science and things like that. So when you talk to a legislator, you are effectively telling that legislator something that may or may not be true, but that legislator will perhaps listen to if he or she thinks that there's a constituency there who thinks the same way as you do. So we have a failing government in California because of that particular reason. So the key thing for nuclear power to understand, which makes it completely different from all the other sources, is power density. That is the key environmental issue. Every environmental, and everybody who thinks they're an environmentalist had better understand that, because I have yet to meet any wind or solar farm advocate who actually is a true environmentalist, because they don't get power density. This is a piece of uranium. It's pure U-238. I'm not going to pass it around because somebody lifted my last piece of thorium last conference. But this amount of uranium runs any American's life for a decade. And the amount of waste it produces even under the current cycle is your pinky nail, right? So, and that's the kind that we could use, or the smallest amount, 4% of that total amount could be stored for a few hundred years and go away. Whereas the arsenic and lead and so forth in Chesapeake Energies or Duke Energies coal piles never goes away, right? So it's important to understand the difference. So power density, instead of 10,000 tons of coal, you've got a little bit of uranium or a little bit of thorium. Same thing, same power density. So, all right, so let's move on with it. Let's move on with this. So we have what I term, I've been doing this for the last few years because in about 2009, it dawned on me, and reading some of the scientific literature that we get sent all the time, that there's a nonlinear effect called ocean acidification, which is leading to extinctions, and extinctions are not reversible. Now, some things may move around when situations change environmentally, as we saw in Dan's example. But if you change things enough, there's no movement of species sufficient for them to survive. And that's the era that we're entering right now in the oceans. So I'm going to whip through this first part. The species that we're concerned with are at the base of the food chain in oceans. The lower center picture of plankton, very small, 1 micron, 10 micron, 100 micron, tiny little things that you don't see all throughout the ocean. That's the base of the food chain. Without those organisms, the only thing that might be left would be some jellyfish. And because these organisms are different in the sense that, from jellyfish, in the sense that they calcify, they take carbonate ion out of the water, build calcium carbonate shells or skeletons like we have, and when they die, they take that to the ocean floor. And that's carbon that's sequestered. The carbon and carbonate ions in the ocean get sequestered when these living creatures die and sink to the bottom of the ocean. And after enough time, the sediment can actually become limestone. That's the important thing. That's the dominant carbon sequestration system on our planet. There's nothing else. Forests do not net sequester carbon because, as we know, leaves fall, trees die, they fall down to the ground, they get digested by soil organisms which emit methane and carbon dioxide. So only if something gets covered as oil or gas deposits have been covered by geologic processes, only then do things get sequestered that are carbon-based. Right? So in generally speaking, there's very little carbon sequestration except from this ocean process. And the ocean process can do a billion tons of carbon dioxide a year. Anybody know how much we emit every year now?
32 billion?
32. Do I hear 33? How about 34, 35? So we are falling over 30 years behind every year on emissions, okay? And this, by the way, is what you see. You see the shell on the upper left? This is a much smaller than the picture. This is a little snail that a lot of sea animals eat. They depend upon it, and its shell is very thin, and it's poked with holes because of the pH, the acidity of the water is lower than it has been in about 300 million years.
You mean the pH is lower?
pH is lower, yeah. Right, it's closer to about 8. We lowered the pH in the Industrial Revolution in all the ocean on average from 8.2 to 8.1. These guys can't handle 8.0 and below. So we're good part of the way there, right? So current emissions are a real problem, but past emissions are there regardless of eliminating any emissions today. If we eliminated all emissions right now, today, all carbon dioxide emissions, there would still be about 1.8 trillion tons of carbon dioxide man-produced in the air and water. And you can look that up by looking at the fossil fuel sales receipts for the last 200 years. You can figure out where that 1.8 trillion tons came from, and you can do an isotopic analysis on it and determine the carbon is fossil carbon. The carbon-14 ratio is very low. Oxygen, again, is recent oxygen. You can tell that from the isotopic analysis as well. So we know we have 1.8 trillion tons that we've put in. We know that the natural cycle can handle 1 billion tons. So that means, and we have about a third of the 1.8 trillion already in the ocean as carbon dioxide dissolved, making carbonic acid, which is where the pH gets dropped. So that means that we have about 1,000 or 1,500 or more years behind. We've fallen that far behind the natural cycle. So we really need to start thinking about this, because the upper graph, note the precipitous drop at the right, that's what we've done, or we're about to do. Whereas if you go all the way to the left, that's about the time whales evolved. All right, so we go all the way to the left, 25 million years, and we go back another 200 million years or plus. We don't find places that have as low a pH as currently. The last time pH was that low was about 250 million years ago during the greatest extinction ever, the Permian extinction. And that was caused, as I mentioned briefly, by some massive introductions of CO2 into the atmosphere as well. But we have actually equaled we have equaled the rate of CO2 production of the events that led to the Permian extinction 252 million years ago. We, as one species on this one little planet, have equaled the worst emissions of carbon dioxide during lifetime's existence on the planet in terms of rate. We emit it as fast as it was being emitted then, which then triggered the greatest extinction. So where the red and the blue curves cross on that graph in the lower left, that's the end of sea life that calcifies. The end of whales, everything else that feeds on that. And the end of about 15% of human food protein sources. So we take 15% of 7 billion people and say, oh, sorry, no more food protein from the ocean. Okay, so that's our situation. And that's why I call this an Apollo 13 moment, because we know exactly when that's going to happen. We know we have 1.5 trillion tons of CO2 in the air that shouldn't be there, and we know the rate at which it dissolves in seawater, and we know how that lowers the pH. So we know almost as exactly as the Apollo people knew how long it was going to take for those guys to die up there from CO2 poisoning. Right? All right, so I'll skip through this. So what do we do? One of the things that we can do is use clean energy to somehow address this falling ocean pH, the increased amount of carbonic acid. And one thing we can do is mimic the natural process that the animals were using to sequester the 1 billion tons a year that they do now and have been. And what we can do is we can use energy to do what cement plants do, for instance. A cement plant takes limestone, which was created by these sea organisms, takes limestone, heats it up, releases the carbon dioxide into the air, and takes the lime to make the cement. Well, we don't want to actually do it the way the cement plant people do it. We want to take the CO2 that we got out of the limestone, which is about 50% of the limestone, which is a lot, much more dense than the air, which only has 400 parts per million. So we can get a lot of CO2 out of the limestone, sequester that, and then take the lime and put it in the, get a Microsoft here, and put the lime back in the ocean where it came from. And that raises the pH gradually. So how much do we have to do? Well, let's go to the basic calculation. So how much do we have to do that? See, this is where all the carbon comes from. The top is electrical energy, coal burning, that kind of thing. Let's go down here. So what can we do? Well, there's people in Iceland and in Washington State where there's a lot of basalt. Basalt is the dark layer there in the right-hand picture. That basalt went through a volcano. It was heated as hot as we heat anything like limestone to make cement, and the CO2 was driven out of it. That's why CO2 comes out of volcanoes, right? So that basalt now is CO2 poor and would like to have some CO2 back. So what they're researching in Iceland and in Washington State is taking CO2 and a little water, pumping it down into porous basalt formations, and bingo, it's back to being carbonate rock. It's not like the left-hand picture where it says, well, we hope that it's not going to leak out of this old oil well that we keep pumping it into, or we hope it's not going to leak out of this old coal mine in Pennsylvania that we're going to pump it into and maintain high pressure and make sure it's not leaking for thousands of years. No, it's going to make carbonate rock. It's going to make the equivalent of limestone in the basalt formation. And fortunately, there's one island off Iceland that has enough cubic miles of basalt to store all our carbon dioxide emissions each year. It's about 10 to 12 cubic miles of basalt is what you need to store our 30 billion tons of emissions every year, right? This then is a great way to sequester permanently. But what do we do? How do we actually get the energy to do it? So I'm going to skip by all the stuff you already know about the superiority of nuclear power. Here's what we do. The bottom red line, we need 90 gigawatts of electricity to run an electric version of the cement plant, about 10,000 of them operating 24/7, we would need about 900 new 1 gigawatt nuclear plants to run enough of these limestone processing plants to give us enough lime to put in the ocean to neutralize our present emissions. That would just keep us even, because remember, we've got 1.8 trillion tons that we've emitted in the industrial age. About 500 billion tons have been dissolved in the ocean, so that means we've got over a trillion tons still left to dissolve in the ocean. So even if we effectively neutralize the 30 billion we're emitting each year, we're still not actually nibbling into the inventory that's continually dissolving into the ocean. So if we want to do more, if we want to actually reverse the decline of pH in the oceans rather than just hopefully stop it, then we would have to have much more clean power to run these sequestration, these limestone and lime producing systems. So this calculation is just to give you a feeling for how big the problem is. People do not actually realize how big the problem is because nobody wants to think about it. Nobody wants to think about the fact that we've emitted more carbon dioxide at a faster rate than occurred during the pre-Permian extinction, where 1 million square kilometers of Siberia became volcanically active. And not only that, because that period was after the Carboniferous period, the coal deposits underground, underneath the more recent Siberian volcanism, ignited. So the coal that had been created in the Carboniferous period earlier and was now underground in Siberia under this 1 million square kilometer area of new volcanism burned and added CO2 for thousands of years. So again, that emission rate from both the volcanism and the burning is equal to our rate today. We have matched one of the world's worst CO2 emission events in the last 300 million years. That's where we need to actually place our emphasis and say, how are we going to do this clean energy thing at the bottom red line? That's 10%. To do 100% of our emissions, or 30 billion tons a year, we need 10 times that. We need at least 900 gigawatt reactors, right? Okay, so this is an example calculation. If you've got a better way to protect ocean pH, step up. But this gives you an idea of the scale of the problem that really is, for the whole planet, an Apollo 13 moment. Because we know the cliff. We know how far the cliff is away. We know we can't stop the cliff unless we deal with ocean chemistry. Okay, so global warming is peanuts. Temperature in 2100 that the IPCC is worried about has no meaning if the oceans are dead in 2050, right? That's the basic reality. So we need to get cracking. Okay, any question? You want to pick?
Got one with the kid here. What's your question?
Yeah, so first of all, I like how you put this calculation. A lot of environmentalists don't seem to own a calculator when they talk about this type of stuff. Oh, sorry, what?
You're supposed to calculate here.
Oh, yeah. But so you're talking about people are like, yeah, maybe if we cranked out renewables as soon as possible, like just windmill to windmill to windmill, maybe we could go carbon neutral. But you're saying we don't need to do that. We need to go gangbusters on nuclear power plants.
Well, carbon neutral doesn't mean anything because, as I said, we already have this 1.8 trillion ton backlog.
So we need to pump it out.
So you need to stop doing it. The first thing they say, when you're digging a hole, stop. And the next thing you need to do is to carefully get a ladder down to yourself. And that's what we need. We need a ladder, which means recognizing the need for the ladder and implementing it, which is where the nuclear comes into. Yeah, back there.
Could we possibly buy some time if somebody were to develop a food chain-based organism that doesn't build a calcium shell?
No, those are the guys who are saving us. In other words, we don't want extinctions to occur, just like the California Native Plant Society doesn't want extinctions to occur. So we don't want to change nature. We want to change, right? Over there, and then I'll get back to you. Yeah.
What possible role could the fertilization of specific parts of the ocean play in CO2?
Oh yeah, that's a good question. So when you put something into the ocean, it better be appropriate.
The question was, what if we fertilized or seeded the ocean?
Right, so if you put something in the ocean, you got to be sure you know what's going to happen. So iron is in poor supply in the ocean typically. But what happens then is that you get things like algae bloom. Well, algae doesn't sequester. It makes hydrocarbon molecules, but when it dies, it gets digested by bacteria. And so the carbon dioxide comes back out. So you need something that's going to have carbonate. You need to protect the carbonate forming organisms. Yeah?
Thanks, Alex. You mentioned a known basalt formation that
Yeah.
would be a place for sequestration.
Right.
If we could provide, suppose we could provide the adequate gigawatt capacity to do the sequestration to bring us level with carbon dioxide, doesn't that finite volume imply a finite amount of CO2 that you could sequester there?
Yeah, the basalt, the question is the basalt, how much basalt is it? There's a lot of basalt on the planet. A lot of basalt. I have a little bit here that people can play with. And you can see how porous some of it is. So you have more basalt. I mean, if there's more basalt on the planet that's equally accessible, then you need to do all of the stuff that we've emitted in history. Yeah.
No, we gotta keep it on target. We gotta get going.
All right.
So thanks.
Talk to me later.
Alex will be here